All right, welcome everybody. In the next set of lectures, we are going to continue talking about linear transformations. And in these lectures, we're going to focus on how we can take any linear transformation and express it in the form of a matrix transformation. So let's just review some of these terms, what we talked about in the last bunch of videos. So we say that a transformation T, which is mapping from Rn into Rm, is a linear transformation if and only if T, when we apply the transformation to a sum of two vectors, so T of u plus v, that is equal to T of u plus T of v. And secondly, when I apply this transformation to some scalar c times the vector u, that scalar can be pulled out from the transformation, and that equals the scalar c times whatever the image of u is. So we can break up addition and we can pull out scalar multiplication from this linear transformation. And as a result of properties of matrix vector multiplication, these two conditions, 1 and 2, are exactly properties that we've shown matrix vector multiplication satisfies. So in the previous bunch of lectures, we showed that any matrix transformation is a linear transformation. And what we're going to show in this video is that any linear transformation can be written as a matrix transformation. So before proving this generally, let's take a look at one specific example. So let's consider the following linear transformation that will denote T, which is going to map from R3 into R4. And we're going to define this map in the following way. Let's say we know that when I apply T to the vector, the standard vector 1, 0, 0, we get 3, minus 1, 1, 0. So we're mapping element, a vector in R3 has 3 entries to some vector which is in R4. So that's why we wind up with an image that has 4 entries in the vector. And the transformation when we apply T to the second standard vector 0, 1, 0, I'll denote that as T of E2, that maps to 0, 2, 1, 3 in R4. And then lastly, we are given that this linear transformation T maps the third standard column vector, which is 0, 0, 1, and we'll denote that as the vector E3. The image of E3 is the vector 1, 0, 1, minus 1 in R4. So the question here is, if we know where E1 goes, if we know where E2 goes, and we know where E3 goes, we can use this information to figure out where T is going to map any arbitrary vector x in R3. And I want to just make another mention about this notation that I've used with E1, E2, and E3. These are called the standard column vectors. These E's are bold because these are vectors, right? So this is a vector where the first entry is 1 and all of the rest are zeros. E2 is a vector where the second entry is 1 and all of the rest are 0. E3 has zeros everywhere except for the third position. So let's see how we can figure out how to map any arbitrary vector x in R3 based on this information. So any vector x in R3, we can write as some linear combination of E1, E2, and E3, because we know that these three vectors, E1, E2, and E3, they span all of R3. So any vector x in R3 can be written as a linear combination of these three vectors. And now we know that T is a linear transformation. So recall, that means we can break up addition from inside of this map, and we can also pull out the scalar multiple. So these x's are just denoting scalars. So from the two properties of a linear transformation that we know T satisfies, we can break up the addition and pull out the scalar multiples, and we get the following form here. And now I can use the information that I know about T of E1, that was over here. T of E2, that is over here in red. And T of E3, we were given over here. So let's use that information next. And I'm going to replace T of E1 with its image that we were given. So that's where the 3 minus 1, 1, 0 comes in. T of x2, so we've got x1 plus the image of E1 plus x2 times the image of E2, which was 0, 2, 1, 3, plus x3 times the image of E3, which was 1, 0, 1, minus 1. And this is how we can define we can think about this as the product of a matrix and a vector. So it would be the matrix whose first column is this vector in green, whose second column is this vector over here, 0, 2, 1, 3, and whose third column is this vector here, 1, 0, 1, minus 1. And we're going to multiply that matrix by the vector x1, x2, x3. So just using what we know about the definition of the product of a matrix and a vector, we can rewrite this vector equation as a matrix equation over here. And so now we can see that here's the image that we get for any old vector in R3. So if I know what the coordinates of that vector is, its first entry, its second entry, and its third entry, then I can figure out where that arbitrary vector gets mapped into R4. So here we have 4 entries in its image. And so notice this linear transformation where all we were given was where does this transformation map E1, E2, and E3. And just given those 3 images, we're able to define the map for all of R3. And notice this map, T, has a matrix representation. The first column was the image of E1. The second column is the image of E2. And the third column in our matrix representation was the image of E3. So we're going to prove this result in general on the next slide. So here we can state more generally the result that we saw in the previous example. So for any linear transformation T, which maps from Rn into Rm, we do have a unique matrix A, and we'll call this matrix the standard matrix for the linear transformation, such that T applied to some arbitrary vector x in the domain, we can write as a vector matrix product, a matrix vector product, as some matrix A times that vector x. And we call this the standard matrix because we're basing this on the standard column vectors that we were introduced in the previous example. And so this matrix A is going to have its first column is going to be what is the image of standard vector 1. Its second column is going to be what is the image under T of standard column 2, and so on. So here we've just written out generally what we showed in the previous example, but let's prove this for the general case. So down below, we've got our proof. So let's take a look at how this linear transformation T would operate on some arbitrary vector x. And again, since x is in Rn, we know that E1, E2, all the way up to En, this forms a spanning set of vectors for all of Rn. So that means any vector x in Rn can be written as a linear combination of these standard column vectors. So any vector x I can write as some scalar x1 times the vector E1, some scalar plus some scalar x2 times E2, all the way up to some scalar xn times the nth standard column vector En. And now, because we were given T is a linear transformation, we can take advantage that we can break up addition from inside of this transformation, and we can pull scalar multiples from inside this transformation to outside. So here I'm just using those two properties of a linear transformation. And now we can use the fact that this is a vector equation that we can express as a matrix equation. as follows. So now we can write this as the first column in our vector, or in our matrix, excuse me, is going to be T of E1. The second column in our matrix is going to be T of E2, and all the way up to the nth column in our matrix is going to be the image of the nth standard column vector. And then we multiply this matrix by the vector x1 up to xn. And so keep in mind that this matrix that we have over here, we're looking at the n different columns. Each of these columns has a total of m entries, right? Because we're mapping into Rm. So this matrix A that we find in the end is going to have m rows and n columns. And here, this matrix A, again, is constructed by each of its columns is going to come from the image of one of these standard column vectors. And this is a really impressive result. Now we know that any linear transformation is a matrix, can be written as a matrix transformation, and any matrix transformation is a linear transformation. So these are identical transformations. So if we understand matrices, then we really can understand how every linear transformation works. So this is a really, really nice, powerful theorem that we get from linear algebra.